This is where the world's most powerful technology is built. Factories operating at atomic precision. Lasers carve billions of transistors into silicon. Atomic layers are stripped and rebuilt, every movement measured in nanometers. This is how AI microchips are built. If you are fascinated by the engineering behind the world's most advanced machines, subscribe to this channel. Now, let's begin. Every AI microchip begins as raw quartz extracted from the earth. The quartz is crushed and processed to isolate high-purity silicon dioxide. Inside electric arc furnaces, quartz is reduced into metallurgical-grade silicon at temperatures above 2000 degrees Celsius. The silicon is chemically purified into polysilicon with purity exceeding 99.999%. A single crystal ingot is slowly pulled from molten silicon using the Czochralski process. The ingot is sliced into wafers, only millimeters thick. Each wafer is polished to an atomically smooth surface before fabrication begins. Each wafer is chemically cleaned to remove microscopic contaminants before circuit fabrication begins. A liquid photoresist is applied and spun at thousands of rotations per minute to form an ultra-thin light-sensitive layer. Ultraviolet light projects circuit patterns onto the wafer with nanometer accuracy. The exposed photoresist is developed, revealing the microscopic circuit design. Plasma etching removes exposed material, carving the circuit into the silicon. Ion implantation alters the electrical properties of the silicon at controlled atomic depths. Each patterned layer is inspected and aligned before the next layer is added. This patterning process is repeated dozens of times to build multiple transistor layers. Ultra-thin gate oxides and conductive layers are deposited to form individual transistors. Extreme ultraviolet light prints features smaller than 10 nanometers. Metal interconnect layers are added to link billions of transistors together. Each layer is polished flat before the next layer is built. Modern chips use 3D transistor structures to increase density and performance. Billions of transistors are packed onto a single chip, no larger than a fingernail. Each wafer undergoes electrical testing to verify transistor functionality. Defective regions are identified and mapped with nanometer precision. The wafer is cut into individual microchip dice using precision dicing system. Each die is mounted and electrically connected inside a protective package. The chip is sealed to protect its circuitry from heat, moisture, and contamination. Each chip undergoes high-speed validation to confirm performance under extreme computational load. Only after passing every test is an AI microchip ready to power the systems shaping the modern world. Every AI microchip fabrication facility operates within one of the cleanest environments ever engineered. Ultra-low particulate air filters remove particles larger than 0.1 micrometers. Laminar airflow continuously pushes contaminants away from exposed wafer surfaces. Positive air pressure prevents unfiltered air from entering the fabrication space. Temperature and humidity are tightly controlled to prevent material expansion and static discharge. Advanced isolation systems eliminate vibrations that could disrupt nanometer-scale patterning. A single microscopic particle can destroy multiple circuits on a wafer. Without extreme environmental control, advanced microchip manufacturing would not be possible. Extreme ultraviolet lithography is the most advanced patterning technology used in semiconductor manufacturing. Microscopic tin droplets are fired 50,000 times per second to generate UV light. A high-energy laser strikes each droplet, creating plasma that emits extreme ultraviolet light. Because UV light cannot pass through glass, it is guided using ultra-precise reflective mirrors. The entire lithography process operates in a near-perfect vacuum to prevent light absorption. The wafer stage moves with precision, measured in nanometers during exposure. Each circuit pattern is transferred through a precision mask aligned with extreme accuracy. UV lithography enables the printing of features smaller than 10 nanometers. Each UV system costs over $100 million and contains more than 100,000 precision components. As fabrication nodes shrink from 14 nanometers to 3 nanometers, transistor density increases dramatically. Smaller nodes reduce the distance between transistor gates, allowing more devices per square millimeter. Reduced transistor size improves switching efficiency and lowers overall power consumption. At extremely small scales, leakage current becomes a significant engineering challenge. FinFET architectures use vertical fins to improve electrostatic control of the channel. Gate all-around designs further improve performance by surrounding the channel on all sides. Modern 3-nanometer chips can contain billions of transistors within a few hundred square millimeters. Not every die on a finished wafer will function correctly. Defect density directly affects the percentage of usable chips per wafer. Higher yield means more functional chips are produced from the same wafer. Manufacturers rely on statistical process control to maintain consistent production quality. Failed chips are analyzed to identify microscopic structural defects. Production optimization focuses on reducing scrap while improving overall yield. Modern semiconductor facilities process thousands of wafers every month. Once packaged, microchips are mounted onto high-performance computing boards. Multiple processors are combined to create powerful AI accelerator modules. These modules are installed into server systems inside large-scale data centers. Under full load, billions of transistors switch on and off billions of times per second. Advanced cooling systems are required to manage the heat generated by dense computation. Together, these facilities form the backbone of modern artificial intelligence infrastructure. What begins as raw quartz becomes the foundation of the world's most advanced computational system.